Good morning to all of you. Welcome to the topics related to the magnetostatics. So the outline of this session is, first of all, we will discuss about the previous year gate problems and solutions on electrostatics topics, which we did in the previous two sessions. And now then we will follow with sources of magnetostatic field, electric current configuration, Biot-Savart's law, Ampere's circuit law, then curl, Stokes theorem, magnetic flux density. Then we will discuss about Maxwell's equation and finally vector magnetic potential. So this is the brief outline of the session that we are going to do in this particular session. So first of all, let us take the previous gate problems on electrostatics. Suppose we are given a problem on two conducting spheres. Two conducting spheres S1 and S2 are given. Their radii are given as radius A and as well as radius B. This is one sphere S1 with radius A and another sphere S2 with radius B is given. And it is clearly given that the radius B is greater than radius A. That means radius of S2 is greater than the radius of S1. That is, the first sphere radius is less than the radius of the second sphere. Are placed far apart. They are placed far apart, and by connected a long thin conducting wire as shown in the figure. So this is what the figure given for us. And now what is the question asked is, for some charge placed on this structure, the potential and surface electric field on S1 are given as VA and EA. So potential on S1 is VA. Electric field intensity that is given is EA. Again, similarly, potential on S2, which is given as VB, and field intensity on the second sphere of radius B is given as EB respectively. Then we are given the options. The following four options are given. Which of the following is correct? Whether the relationship between the potential of sphere A and sphere B and the relation between the two electric field intensities EA and EB were given in various options, and which of the options is correct? This is the question given. Now we will see the solution for this. The two spheres are joined with a conducting wire. So because the two spheres are joined with a conducting wire, the voltage on the two spheres is the same. Do you agree or not? Between the two spheres which are conducted with a wire, what happens is the potential on A and the potential on B becomes the same as these two spheres are conducted by a wire. And hence we may take VA is equal to VB. VA is equal to VB is one solution. Now we have equation for capacitance of the sphere is proportional to the radius. This we already discussed in the previous session, that the capacitance of the sphere is proportional to the radius. Hence we may take capacitance of the sphere A is proportional to A, capacitance of sphere B is proportional to the radius B. Now take the ratios of capacitance of A and capacitance of B. It is equal to A by B. And we are aware of the equation Q is equal to CV. Just make use of that equation and take the ratio of QA by QB is equal to CA by CB, capacitance of A divided by capacitance of B, as potential VA and VB being the same. Here in this equation, both the numerator potential term VA and the denominator potential term VB gets cancelled as they are equal. Hence we get here A by B as the ratio. Now we may find electric field intensity along on the sphere A, and similarly electric field intensity on B using the equation 4 pi epsilon Q by A square and 4 pi epsilon 1 by 4 pi epsilon Q by B square, and Q and Q being the same, here you need to take care that this is Q charge, right, and this is also. So here you get the ratio as A by B, and this A by B being greater than unity, epsilon EA, that is electric field intensity on A, is greater than electric field intensity B. So we got the answer as B in answer as C, where we have potential on sphere A and sphere B being the same, and field intensity on A is greater than B. This is the first problem that we can observe from the previous gate questions. And now let us move to the second question. An electron Q1 is moving in free space with velocity 10 power 5 meters per second towards a stationary electron Q2 far away. Okay, so you have an electron Q1 that is moving in free space with a velocity of 10 power 5 meters per second towards a stationary electron. So there are two electrons with charges Q1 and Q2. One is stationary, another stationary one is Q2, and another one is moving with a velocity Q1. So the closest distance that is moving, the closest distance that this is moving, electron gets to the stationary electron before the repulsive force diverts its path is. So we are given mass of electron m is given, charge of the electron is and permittivity are given. So these are the given parameters. So we need to find out the closest distance that this moving electron gets to the stationary electron before repulsive force diverts its path is. Already units are given 10 power minus 3 meters, and here we have to find how much is the distance. Now work done due to the field. So we have derived this equation also in the previous session. Work done due to the field and external agent must be 0. So which is given by QV is equal to half mv square. So here we may equate, this is QV is equal to half, charge is given for us, we may use this identity as, why do we get half mv square? Observe that the electron Q1 is moving with in free space, so its kinetic energy is given by half mv square, and QE is the energy of this one, and substitute in place, okay, can be substituted, and half m v square is given for us. Yeah, what is given for us is 10 power 5 meters per second. So working with that, you may find this R, this is the distance 1 by 4 pi epsilon R, this is R, okay, which is given by 5.08 10 power minus 3 meters. So law of conservation of energy can be used for solving such problem. Now let us take another important problem. There are concentric spherical shells of radii. So how many concentric spherical shells are given? 3 concentric spherical shells of different radii. One is with 2 meter, second one is with 4 meter radii radius, and the third one is with 8 meter radii. They carry uniform surface charge densities. Their charge density, as you are aware, units for charge densities are coulomb per meter square, 20 nanocoulomb, another one is minus 4 nanocoulombs, and rho s respectively. The value of rho s, so observe that for the third concentric spherical shell, the charge density was not given, numerical value is not given, and we are asked to find that numerical value, the value of rho s nanocoulomb per meter square, which is required to ensure that the electric flux density d bar is equal to 0 at radius 10 meter. So you are supposed to find the flux density at a radius of 10 meter, and you may use all these charge densities and the radii values of these concentric spherical shell. So this is what the given problem. So how do we attempt it? So consider a Gaussian surface of sphere of radius 10 m. So whenever we want to apply the Gauss law, the important concept of the Gauss law is we should have a closed surface. So consider a Gaussian surface of sphere radius 10 meter. To ensure that flux density is 0 at radius 10 meter, the total charge enclosed by the Gaussian surface is 0. So we have to use integral d bar dot ds is equal to the charge enclosed. So these are the double integrands, and the d bar dot ds bar is equal to the charge enclosed, q enclosed, qen, okay, which is given here. This should be 0. Okay, this should be 0. So this is what the equation that we use in order to find out the charge enclosed. So how do we get the charge enclosed is what is given. The surface charge densities are given. So what are the units for surface charge density? Then you are going to get your 20 nanocoulomb, that is 20 into 10 power minus 9 multiplied with, okay, 2 square, radius square. So coulomb per meter square into meter square. So we are left with coulombs. So left hand side the units are coulombs, and also right hand side you will get the units as coulombs. So another second sphere has the charge density as minus 4 nanocoulomb. That is the reason why here you got minus 4. Minus 4 multiplied with radius square, which is radius is given as 4 meters for the second one. So you substitute that 4 meter. And the third is rho s. So here is rho s is the surface charge density for the third one. Okay, so rho s into, again you have the radius square here, and you equate integral d bar dot ds, which is charge enclosed to 0. So that is what you are doing. As a result, you may find the value of rho s as 0.25 nanocoulomb per meter square. Do observe here into 10 power minus 9 nanocoulombs is common for all the charges. Okay, here we have not shown explicitly, but in the problem it is clearly given 20 nanocoulomb per meter square and minus 4 nanocoulomb per meter square, and rho s can be computed as minus 0.25 nanocoulomb per meter square. Very easy. So if you remember the concept of Gauss law, so you may not be asked directly the question based on the Gauss law. You may be asked like this, but you are making use of the concept of Gauss law in order to solve such problems. Next, the region specified in cylindrical coordinates has the volume. So you observe what are the cylindrical coordinates that are given is rho is the radius, phi is the angle, okay, and z is the component in the z direction. Rho is the radius vector. Rho is varying. The lower limit is 3 and the upper limit for rho is 5. Rho is varying from 3 meters to 5 meters. Phi phase angle variation is from pi by 2 to pi by 4. That is what is given. And this is a very easy problem. And z is given, it is varying from 3 to 4.5. So what, just think for a few seconds what equation can be used for solving this volume. You are aware, differential volume integral dv, triple integral, in which you may get, okay, we discussed in the previous sessions H1, H2, H3, the scale factors. The scale factors, variation of rho is linear, hence 1 into d rho variation. 1 into variation along the radial direction, which is d rho. Variation along the rho direction is d rho, and the scaling factor is 1. Now the question is, why scaling factor 1? We have discussed the variation of a rho, which is a radius, is a linear side. Hence the variation is a linear variation and your scaling factor is 1. Now, what is the second one? Phi is a phase angle. So, variation is dou phi. Is the dou phi variation is linear? No, it is non-linear. It is of the form arc length L is equal to R into theta. Number of times. So, the scaling factor H2 is rho here. Variation along the z direction is dz. Scale factor is 1. So you may observe the scaling factors H1, H2 and H3 as 1 into 1 rho and 1, and for volume d rho, rho d phi, dz, dv can be taken. So that is what is taken. That is how we got rho d phi dz, and you substitute the lower and upper limits, and the integration need to be done with respect to rho and with respect to phi and as well as with respect to z. So there is no z term. Integral dz is z, and hence you may get z straight away. Lower and upper limits are given 3 and what is given 4.5 meters for z. Just substitute those limits. Phi variation, integral d phi is phi. Limits given as pi by 2 and pi by 4, so you may easily find. Integral of rho d rho, this is of the form integral x dx. So x square by 2, here rho square by 2, and upper and lower limits can be easily substituted as 3 and 5. You may get easily the value as 1.5 pi as the volume, and what are the units? So what is missing is the most important one here is meter cube. So you need to find that actually. So 1.5 into pi 3.1415, and here you must include the units of meter cube. So that is what the important problem. So the current density in a medium. Next problem. The current density in a medium J bar is given by this equation. The total current and the average current density of the following portion of a spherical surface. We are given a spherical surface. For spherical surface, essentially we require R, phase angle theta, another phase angle phi. They are given for us respectively. Now we are asked, we are given current density J, okay, in a medium which is given. The total current and the average current density are asked in the problem. So how do you deal with this one? Is current density J is given. Current passing through the portion of sphere of radius R, J dot ds within a unit area is your current density multiplied as a J bar. So you need to take here AR bar. What is AR bar? Is along the radial direction. So you may take the differential surface areas in 3 manners. 3 particular differential surface areas are possible with your spherical coordinate system ds1, ds2 and as well as ds3. But in our case, whatever the differential surface area along the radial direction only need to be taken. Reason being, AR bar dot producted with A theta, AR bar dot producted with A phi is going to become 0, but only the dot product with AR bar itself only does exist, right? And hence what is to be done is you need to take the ds bar along the radial direction. So j bar is taken along the radial direction, that is dot producted with the ds bar, again that is in the AR bar direction. AR bar dot producted with AR bar is resulting in a unity value, whatever this 400 sine theta divided by 2 pi multiplied with r square plus 4 was taken as the j value. R square sine theta d phi is the differential surface vector that was taken here. Now you may integrate, and yeah, as a result we are going to get 7.45 amperes. So the average current density, we are asked about current and as well as average current density. So the average current density through the given spherical surface is given by this equation. Area of the sphere with radius 0.8 meters. It was clearly given for us. So we may take this as for differential volume of a spherical surface. How it is given is dV is equal to, what is differential volume? Is dV is equal to r square sine theta d phi. So r square sine theta d phi. So you got this 0.8 whole square, and the variation of theta is pi by 2 to pi by 4, and phi variation is 0 to 2 pi. Why we have taken the limits like that is here clearly it was given for us. The limits, wow, spherical surface, its radius of the spherical surface is given, variation of theta is given, variation of phi is given. We are taking those those limits here. You observe the same limits are being repeated here, and then you may find your average current density as this value. Now a vector p bar is given, right, and x cube y ax bar minus x square y ay bar minus x square y yz az bar, which of the following statements is true? And p bar is a solenoid but not irrotational, p bar is irrational but not irrotational but not solenoid, p bar is neither solenoid nor irrotational, p bar is both solenoidal and irrotational. Actually we are going to get these concepts in the topic today we are going to discuss, that is magnetostatics and current related, but we may take up this with the concept making use of this. P bar is given as x cube y ax bar x square y square ay bar minus x square yz az bar. For a solenoid, del dot p is equal to 0. We will discuss in detail about how this identity we got. Okay, del dot p can be computed as the dot product between the del vector and the p that is given dou by dou x of px, dou by dou y of py, dou by dou z of pz or rho z. So you may take this as 3x square y minus 2x square y x square, differential of x cube y with respect to x is 3x square. So we got 3x square y here. Differential of, yeah, x square y square with respect to y. So x square is treated as a constant. Dou y of y square will result in 2y. So hence you got yz. So x square y dou by dou z of all the terms you have x square and Y. So hence P bar is solenoid, and the curl or the cross product between del square, del bar and P bar, curl of P bar is not equal to 0. So we may observe curl of P bar, it need not be computed, we may easily do this, and we observe that del cross is not equal to 0, and hence you may conclude the answer as solenoidal and but not irrotational. So this is what we may understand. Now the most important concept again, capacitance based. The parallel plate capacitor is shown in the figure, has movable plates. So these plates are movable, that is what given. The capacitor is charged so that the energy stored in it is E. When the plate separation is D, the when the plate separation is D, that is what given. The capacitor is then isolated electrically, and the plates are moved such that D is the distance, the plate separation becomes 2D. So beginning the plate separation is D, then the plates are separated by a distance of 2D. At this new plate separation, what is an effect stored in the capacitor? Neglecting fringing the energy. This is what is given in the problem. So we need to understand this carefully. If the capacitor is electrically isolated, then the charge is the same. The concept that we have to use is, if capacitor is then the charge is same. That is Q1 is equal to Q2. The charge is the same. And yeah, we are very much aware of C is equal to epsilon A by D. C1 is equal to epsilon A by D1, and C2 is equal to epsilon A by D2. So C1 D1 is the same as that of C2 D2. As we made this, if the capacitor is electrically isolated, then the charge is the same. And as a result, and C1 V1 is the same as C2 by V2. So if D is doubled, so if the distance is double, then what happens? C will be C by 2 and V will be 2V from these two relations. Okay, is it clear? If D is doubled, the distance is doubled, then the capacitance C will be C by 2 and V will be 2V. Given, what is given? E is equal to half CV square. Okay, this is half CV square. 1 by 2. In place of C, the new charge, which is new capacitance, if the distance is doubled, it is C by 2. So C by 2, and how the potential is varying, potential is getting doubled, capacitance is getting halved. Why this is happening is, the distance, earlier the distance is D, now the distance is doubled between the plates of the capacitor. Okay, 2D. Okay, D is the distance of separation between the parallel plates of the capacitor in the earlier case. Now 2D is the distance of separation presently. As a result of variation in distance of separation between the parallel plates of the capacitor, the new capacitance value is getting halved and the potential is getting doubled. As a result, you got this value as 4V square. Okay, 2 square, 4, 1 by 2 and C by 2, and you got the answer as this. Okay, and now a positive charge Q is placed at x is equal to 0 between two infinite metal plates placed at x is equal to minus D and x is equal to plus or minus D and plus D respectively. The metal plate lie in the YZ plane. The charge is at rest at t is equal to 0 when a voltage plus V is applied to the plate at minus D and voltage minus V is applied to the plate X is equal to plus D. So you observe a positive charge Q is placed at X is equal to 0. So this is X is equal to 0. Between two infinite metal plate. This is one metal plate. This is the another metal plate. So two metal plates are placed at X is equal to one is at X is equal to minus D. Yeah, this is at X is equal to minus D. This is at X is equal to plus D. The metal plates lies in which plane? YZ plane. It is given clearly, metal plates lie in YZ plane. The charge is at rest at t is equal to 0. Okay, charge is at rest, that is given at t is equal to 0. When a voltage plus V is applied to the plate at minus D. Okay, for the plate that is located at X is equal to minus D, a voltage plus V is applied. A voltage plus V is applied to this particular plate at minus D, and voltage minus V is applied to the plate at X is equal to plus D. So for the left hand side plate, this is located at a distance X is equal to minus D, plus V potential is applied, and at X is equal to plus D, for this one my charge or delta Q you may say, the time that charge Q takes to reach the right plate is proportional to. So we are asked about the time that charge Q takes to reach the right plate is proportional to. Now let us draw this one. What is given? The metal plate lies in the YZ plane. So what is the equation for YZ plane is, you may observe YZ plane equation is X is equal to 0 is the YZ plane. So this is your YZ plane that was taken. So one plate is at a distance plus D, X is equal to 0 is at the origin, and yeah, this upper plate is located at a distance plus D, that is to the top, and the applied potential is minus V. Fine. Again, take the second plate. The second plate is located below the origin at a distance minus D, and the applied potential is plus V. This is how we can visualize the given problem statement. So this is the visualization of the given problem statement. So I think it's very clear for us. When there is no external field, so external field was not applied, charge at rest having potential energy only P into E, potential energy. PE means potential energy, and is equal to Q into V. By an external field, charge acquires some charge carriers acquire some kinetic energy with velocity V. This is the reason why in the previous problem also we equated this QV is equal to half mv square. If you remember, we used the same equation where m being the mass and v is the velocity. So half mv square is equal to this. Do remember here, this is your V. What is this? V is your potential. So don't get confused between this V and this V. This is your potential. So V is equal to velocity V is equal to square root of 2e V electron volt or charge Q into V. Product of this we just replaced with Q with E in this equation. Nothing new. Square root of 2qV by m. Time taken to reach X is equal to D plate is known as, let us take GTR is the distance, is the time taken to reach X is equal to D plate. Time taken by the charge to read. What is asked in the question is the time that charge Q takes to reach the right plate. So right plate, let us take that time taken as T or something, gap transit time. It is defined as gap transit time, or Tg. So we may take a flexible notation or convenient notation like Tg, and Tg is given by, this is a well-known equation. Okay, so how we get this equation is velocity is equal to your distance divided by time. So a known equation, nothing new. T is equal to distance by your velocity v, and the distance divided by, in place of velocity we may substitute square root of 2 into qv, where qv is the charge. In place of the charge we have e. Distance may vary, so t gap transit time, or td delay time, or gap transit time, tg, any notation can be taken, is proportional to distance divided by square root v. So in the given options, distance divided by square root v. So here the C, option C is correct answer for this one. So you have to apply this important concept so that you can easily find out. So in a source-free region in vacuum, so we are given a source-free region in vacuum. If electrostatic potential is given as this notation, so given in the problem, phi is given as 2x square plus y square plus cz square, the value of constant c. Observe here, you got a constant in the equation cz square, the value of the constant c must be, we are asked to find this one. So again, think a while what equation or concept is to be applied for finding the solution for this one. Given electrostatic potential as phi, we are taking appropriate notation, okay, in the solution for our easy understanding. Though in problem something was given, we will take our comfortable notation. So given electrostatic potential, phi is equal to 2x square plus y square plus cz square. The electric field is obtained is equal to minus del dot, yeah, this is 0. Because of why you are getting here 0 is it is a source free region. So just substitute your given E, that is potential. Actually potential is given, electric field intensity, we have this equation del dot E as minus rho v. In that we are substituting, in place of electric field intensity we are substituting simply del phi. So substitute that one here. So we may get, how do we get that is dou by dou x of 2x square is 4x. So hence here we got 4x. Dou by dou y of y square 2y, we got it. Dou by dou z of cz square is 2cz, we got 2cz here. And that is to be dot producted with, yeah, with del operator. So del operator is, again we are aware, substitute the del operator, dou by dou x of minus 4x is minus 4, dou by dou x of dou minus 2 you will get, and dou by dou z of an infinite grounded metal plate in a medium of permittivity epsilon is. So it seems to be a very simple question, but do remember this is an in-depth question and this needs the thorough understanding of boundary conditions, and also an important new concept called method of image is required to solve such problem. So what is the prior knowledge required for solving such problem is method of images and boundary conditions. Okay, this is a little bit tough question, but we will try to understand it in a easier manner. So how do we understand? The concept of method of image is required. The effect of the boundary is replaced by one or several equivalent charges, and the original inhomogeneous region with a boundary becomes an infinite homogeneous space. And the principle, what is the basis is, the principle of uniqueness is the basis for this. What is that? Therefore, the charges should not change the original boundary conditions. These equivalent charges are the image positions of the original charge and are called image charges, and this method is called the method of images. So let us try to understand this method of images. Okay, so what is the key is to determine the values and the positions of the image charges. So the concept of method of images is required for solving this problem. Hence, we are additionally learning this concept of method of image. Okay, what is the restriction is, these image charges may be determined only for some special boundaries and charges with certain distributions. Okay, so a point electric charge and an infinite conducting plane are taken. So a point charge Q and the point P, which is located at a distance R, are taken. The effect of the boundary is replaced. The boundary is replaced by a point charge at the image position. You observe, actually Q is there. The image position of the image charge is Q dash here. While the entire space becomes homogeneous with permittivity epsilon, then the source of dielectric potential at any point P will be due to the charges Q and Q dash. Okay, so Q dash is an image charge, so that total net potential can be computed making use of phi or potential Q by 4 pi epsilon r. Because of this and because of the image charge Q dash by 4 pi epsilon r dash. Considering the electric potential of infinite conducting plane is 0, we have so why we the electric potential of an infinite conducting plane becomes 0. So this becomes 0. So equate this to 0. So what happens? Q dash is equal to minus Q, provided R is same as the R dash. The distribution of the electric field lines and the equipotential surface are the same as that of electric dipole in the upper half space. The electric field lines are perpendicular to the conducting surface everywhere, which has 0 potential. And electric charge conservation is very important. When a point charge Q is above an infinite conducting plane, the induced opposite charge. See, why we will get Q dash is an opposite charge get induced. When a potential charge Q is above an infinite conducting plane. Yes, this is the case that we are dealing. This is an infinite conducting plane. Above the infinite conducting plane, a charge Q is located. Because of this charge, in the method of images, the concept is what happens? An opposite charge get induced. The induced opposite charge will be distributed on the conducting surface, and the magnitude of the image charge should be equal to the total induced charge. We can also prove the claim by making use of the relation between the charge density and electric field intensity, or the derivative of electric potential on the conducting surface. The above equivalence is established only for the upper half space, for which the source and boundary conditions are both unchanged. Okay, and this is the concept of method of images that we may use. Yeah, and we can prove when an infinitely line charge is nearby an infinite conducting plane, the method of images can be applied as well based on the principle of superposition. So superposition means the net potential or the net potential or the net charge can be found out. Okay, so we will make use of the concept of this method of images for solving the given problem. Why we will use the method of images concept for solving this problem is, observe the surface of an infinite grounded metal plane in a medium of permittivity epsilon is given. So this remind you about the concept of method of images. Now for solving this problem, we have done a detailed discussion of method of images. So now let us look at the solution for this particular problem. So in this particular problem, what was given is a charge plus Q is located at a distance d about a infinite metal plate, and that is connected to a zero potential. And using the concept of method of images, an equal and opposite charge get induced here. So here the charge, as the charge gets induced here, so you got here Q here. Since the charges are and they are opposite in polarities, the force between them may be attractive, and then you may find the solution for this as just make use of the equation. For what is the equation given? The equation is Q by 4 pi epsilon d square. 4 pi Q is equal to what is asked for us is the force being asked in Q by 4 pi epsilon d. So you observe that two charges are there here in the diagram, plus Q, and another one is minus Q. Distance of separation is d from origin to, distance of separation is d from origin to the charge that is having plus Q charge, and minus this is again, this charge is located at a distance d. So the total distance of separation from the origin is between the two is your 2d. So Q is here, minus Q is here. Just now make use of F is equal to 1 by 4 pi epsilon Q1 Q2 by d square equation, and then you may easily solve. So, but the important thing is that method of images concept you have to apply as you are having an infinite metal plate that is connected to the ground. The charge Q will induce another charge here. If that concept is clear for you, you may easily solve this problem. So given the vector A cos x sin y and sin x cos y. So this is Ax bar and this is Ay bar. So Ax bar is the vector along the x direction and Ay bar is the vector along y direction, unit vector along y direction, where Ax bar and Ay bar denote the unit vectors along xy directions respectively, clearly given. The magnitude of curl of A. So this is a straightaway problem. So there is no big logic involved in this one. This is a simple problem only. So one may easily solve curl as Ax bar, Ay bar, Az bar, and del cross A. So del operator dou by dou x Ax bar, dou by dou y Ay bar, dou by dou z Az bar, and cos x sin y, sin x cos y, and this is 0. Now Ax bar multiplied with dou by dou y of 0 is 0. Dou by dou z of sin x cos y. This term, entire term is independent of the variation of z. Hence, you may get 0 here. Now, ay bar dou by dou x of 0 and minus dou by dou z of cos x sin y. So that is also not resulting in anything. Now you take again ay bar is over az bar, this column, dou by dou x of sin x cos y. So cos y is a constant, bring outside the differential, dou by dou x of sin x will result in cos x. So dou by dou x of sin x cos y is resulting in a value of cos x cos y, cos x and cos y, dou by dou x of this. Similarly, dou by dou y of cos x sin y, the minus dou by dou y of cos x sin y. So cos x is independent of the variation of y, hence cos x, dou by dou y of sin y is cos y. So cos x cos y minus cos x cos y is equal to 0. Hence the entire curl of a bar is 0. So that is what the answer A here. Simple problem, so nothing required. Now another problem. A region shown below contains a perfect conducting half space and air. The surface current Ks bar on the surface of the perfect conductor Ks bar is used for representing your surface. The surface current Ks bar on the surface of the perfect conductor is Ks bar is equal to 2x square ampere per meter. The tangential magnetic field in the air just above the perfect conductor is given by this. So now you need to apply the concept of boundary conditions, particularly for this one. Okay, so what are given? There are two mediums. Observe in the diagram itself, air is one medium, and perfect conductor is another medium. So there are two mediums. Observe, this is your perfect conducting medium that is given, air is another medium, and your Ks bar is shown here. So now the question comes, how should I know I have to apply boundary conditions? When you have two media, that two different media, one is a perfect conductor media, another one is a air media, it clearly indicates that we need to apply boundary conditions. Now we based on the concept of boundary conditions. If you do remember, in the previous session we have derived the boundary conditions, and we will make use of the concept of that boundary conditions for solving this particular problem. So based on the boundary conditions, in the problem itself, the surface current Ks bar on the surface of the perfect conductor is given by this 2ax bar. It is 2ax bar. Okay, so be aware. So though it is given 2x bar, for our comfort we have to take 2ax bar is a unit vector along the x-axis direction. Okay, 2x cap is given. What is that x cap? Is nothing but a unit vector along the x-axis direction. Unit vector along the x-axis direction. So take that. What is given in the problem itself is this. So it is the boundary between the two media are given for us, perfect conducting media, and another one is the air media. From the boundary conditions, H1 minus H2 cross producted with unit vector gives us Ks. So H1 minus H2 is equal, multiplied with A is Ks. And from so medium 2 is given as air. Okay, and your H1 is equal to 0, therefore H1 is equal to 0. From the boundary conditions, you may find H1 minus H2 cross producted with unit vector is as Ks, and H1 is equal to 0, and your normal vector is taken as Ay bar, H1 minus H2 An. There An is a vector normal to your H1 minus H2. Then only we can do the cross product, means they are perpendicular, right? So you are going to have, in place of H1 I am substituting 0. Why I am substituting 0? As the second medium is air, we are substituting that. Minus 0 minus H2, okay, cross producted with Ay is given as 2Ax bar. In the problem itself he has given this as 2Ax bar. What is 2Ax bar? Ks bar is equal to 2Ax bar is given in the problem itself. We are just left hand side H1 minus H2 cross producted with your Ay is equal to 2Ax bar. In place of H, we may write H will be having what? 3 components. Hx is the component along x direction. So Hx Ax bar. So we are replacing H with or H2 with Hx Ax bar plus Hy Ay bar plus Hz Az bar. So this is what we substituted in place of H2. If you observe here, this is what we did here. I think you are able to understand this. That is cross producted with Ay bar. Why Ay bar? Observe here, your normal to this is y bar direction, or perpendicular to this is Ay bar direction. So hence observe that in the cross product Ay bar is taken. Now the question is, why not Ax and Az? The answer is this. This is the Ay bar vector is normal to this or perpendicular to this given one. So you replace your H with Hx Ax plus Hy Ay plus Hz Az cross producted with Ay bar, and what is given for us is that is equal to Ks, that is equal to 2As is given in the problem itself. So we are equating it to 2Ax, and and when you cross product Ax bar cross producted with Ay bar, and cross product you remember that it follows your clockwise. Ax bar cross product with Ay bar will result in Az bar. Ay bar cross producted with Ay bar, okay, is again, so A cross B, what is it? AB sine theta. Okay, phase angle between the vector with a vector itself, 0, sine 0, 0. So you may not have any Ay component in the resultant. Similarly, Hz Az cross producted with Y, Z with Y, you observe. So so it is not Y with Z. So here Az cross producted with Ay, that is resulting in minus Ax, again already minus sign is there. So minus into minus plus, so you will get Hz Ax, and what are the components that does exist is These are the components. AX cross producted with AY will result in a AZ component. AY cross producted with AZ result in a AX component. So you have both AX and AZ components. But what is given on the right hand side? 2AX. So automatically which components become 0? Whatever the component we have computed, that Z component becomes 0. So this will not be there. This is 0 as we are equating to 2AX. So your AX bar, HX AX bar is equal to HZ AX bar is your 2AX, and HZ value is equal to 2 and H is equal to 2AZ. So 2AZ bar, in place of AZ bar we have Z cap. So your correct answer is D. So you have to be thorough with the important concepts like boundary conditions, method of images, all these. So you may observe that if at all, if an easy problem comes, that is like straight away curl of A is asked, your job is very easy. Del cross A is equal to, you may find out easily. A is given, del cross A was asked, you may compute. But when you are given such problems, you should be a little bit cautious. You need to apply the appropriate concept. Like here we have applied the concept of boundary conditions. In a similar manner, earlier for one problem based on method of images we did. Now the next problem, the electric field between 2 points A and B is shown. Electric field between 2 points A and B is shown here, and let Xi A and Xi B be the electrostatic potentials at A and B respectively, and we are asked the difference in the electrostatic potential in volts. Observe here the diagram is given like this, and 40 kilovolt per centimeter, that is 10 power minus 2 meter. Similarly here 20 kilovolt per centimeter, as this is at the lower potential 0 kilovolt per centimeter, and here A is given, here B is given, and the distance of separation between the two is given as 5 micrometer. This is what is given for us. A is having, at A, what is the potential is 0 kilovolt per centimeter. So, and the other point from here to here, from this point to this point, we have variation from 0 kilovolt per centimeter to 20 kilovolts per centimeter. So volt per meter, what is the, for which volt per meter or the units is your potential V has volt per meter. See, electric field intensity is volt per meter. V is potential volts. E is equal to V by D. Electric field intensity E is equal to V by D. Hence, this is given for us. Okay, we are taking like that field intensities, and similarly B has 5 micrometer is the distance, and what is given 40 kilovolt per centimeter. So 40 kilovolt per centimeter, here centimeter is there, that came here, so just I am correcting this, 40 kilovolt per centimeter. Okay, that is given for us, and now what is to be done is E minus 20 is equal to, okay, potential is 40 minus 20 divided by 5 into 10 power minus 4 micrometer, 10 power minus 6 and x minus 0. As a result, we may find E as 4 into 10 power 4x plus 20, and we may use the concept of VAB is equal to integral E dot dl concept. We may use this concept. And electric field intensity, just now we computed it as 4 into 10 power minus 4x plus 20 may be substituted here. In place of dl bar, we may substitute this dx. So we may easily compute this integral varying from 0 to 5 into 10 power minus 4. Okay, so observe that if all are maintained in per centimeter or all need to be maintained in meters, so you need to convert into SI units. So you may compute the value of VAB as minus 15 volts. That is very easy to solve this problem. Given F is equal to ZAX bar plus XAY bar and YAZ bar. If S represents the portion of the sphere for Z greater than or equal to 0, then del cross F dot ds. We are asked about del cross F dot ds is. Observe that it consists of this del cross F dot ds, and you may apply del cross F dot ds, we may apply Stokes theorem. Okay, so if you apply Stokes theorem, del cross F dot ds is equal to F dot dl. Okay, this is can be easily converted into a simple integral here, F dot dl. What can be used for doing such? This one is, you may use the Stokes theorem that we discussed in the previous session. Stokes theorem we have in fact derived, and del cross F dot ds is equal to F dot dr. What is given in the problem is x square plus y square plus z square is equal to 1 for z greater than or equal to 0. So, and x square plus y square is equal to, so if you want to apply for a closed curve, x square plus y square is equal to 1, and x can be taken as cos theta and y is equal to sin theta, and theta need to be varied from 0 to 2 pi. So what is to be done is F dot dl, that is going to result in what value? Z dx plus x dy plus y dz, and this is going to be x dy, and that is replaced, x is cos theta, so we have taken cos theta, dy is cos theta d theta, so dy, differential of y is sin theta is taken as y is equal to sin theta, so it is dy is cos theta d theta, so we replaced y with dy with cos theta d theta, and this can be understood as 1 by 2. Now apply this is of the form cos A cos B, so 2 cos A cos B. So you may apply sin of A plus B plus sin of 2 cos A cos B. So you apply that, and then sin 2 theta by 2 and 1 by 2 theta plus sin 2 theta by 2, and yeah, you may get this easily with the lower limit being 0 and the upper limit being 2 pi. Pi is 3.14. So the direction of a vector A is radially outward from the origin. and A is given for us as k r power n, where r square is x square plus y square plus z square, and k is a constant. The value of n for which del dot A is 0. So n value is being asked for us. So basically what is to be done is we need to find del dot A. We are aware of del operator. Okay, r square is given as x square plus y square plus z square. Just mod A is equal to kr power n, and A bar is kr power n, r power n, ar bar. It is radially outward. That A bar is radially outward. Hence, we may write here ar bar, and del dot A bar can be done in spherical coordinates. Why in spherical coordinates is here radially outward. AR bar is radially outward. So del dot A can be easily found as 1 by r square dou by dou r of r square AR, 1 by r sin theta dou by dou r of A theta sin theta, and 1 by r sin phi dou by dou phi of A phi. How we got this is del dot A in spherical coordinate system is again the concept of scale factors h1, h2, h3 is to be used. h1 being 1, h2 being r, and h3 being r sin theta. These are the scale factors used in which coordinate system? In spherical coordinate system. We will make use of these scale factors. And del dot A, how do we get is, so this is dou by dou u of, okay, when we are doing for this one, we have to use h1 as well as h1, h2, 1 by h1, h2, h3. Okay, and then del dot A is dot product with this one. So you are aware of this one. Del dot A is 1 by r square dou by dou r of r square AR, 1 by r sin theta dou by dou r of A theta sin theta, and 1 by r sin phi dou phi by A phi. You may find easily del dot A, making use of this del dot A identity here. Del dot A is equal to k by, we may obtain k by r square dou by dou r of r power n minus 2. So dou by dou r of r power n, del dot A will be 0 if dou by, when it is given del dot A is equal to 0. Only thing is del dot A, how to write del dot A in spherical coordinate system. If you are aware, solving this problem is very easy. So in the previous sessions, if you observe, we have given a clear del dot A equation. Okay, dou by dou r of r power n minus 2 is 0 if r power n minus 2 is a constant, and this is possible if and only if your n plus 2 is equal to 0 or n is equal to minus 2. So you may easily solve this one. Okay. And now what we will do is, this almost finishes your problems, previous gate problems on electrostatics is over. Now we will start the concept of magnetostatics. Okay, so if you remember, in the previous session we have done a detailed analysis of overview of electromagnetic. The fundamental laws of classic electromagnetics are taken, two special cases: electrostatics, magnetostatics, then electromagnetic waves, and geometric optics. Okay, now we are interested in this particular portion. We are now doing a detailed analysis of magnetostatics. The magnetostatic is the branch of electromagnetics dealing with The effect of electric charge in steady motion. The fundamental law of magnetostatics is Ampere's law of force. And the Ampere's law of force is analogous to Coulomb's law in electrostatics. So what are the analogous quantities? Ampere's law of force, it is analogous to Coulomb's law. Okay, Coulomb's law is analogous to Ampere's law of force in magnetostatics. So electrostatics and magnetostatics. In magnetostatics, the magnetic field is produced by steady currents. The magnetostatic field does not allow for inductive coupling between circuits or coupling between electric and magnetic fields. And what are the different sources of magnetostatic field? So the magnetostatic field may get originated due to a constant current, or a permanent magnet also creates magnetostatic field. Electric field changing linearly with time may also produce the magnetostatic field. So magnetostatic may get originated from constant current, it gets originated from permanent magnet, it gets originated from electric field changing linearly with time. Now we just make a comparison between the electrostatic and magnetostatic fields. As we already discussed about electrostatic field in the previous session, we may take the analog quantities or parameters between electrostatic and magnetostatic fields. For the electrostatic field, the source is static charge. You observe, this is source is static charge for electrostatics. For magnetostatics, what is the source? It is the steady current. And for electrostatic, the field is represented in electrostatic, electric field intensity capital E bar and electric flux density capital D bar. Similarly, in the magnetostatic field, we represent magnetic field intensity with H bar and magnetic flux density with B bar. So these are the two important analogous parameters in both electrostatic and magnetic. In electrostatics, we use permittivity, epsilon as the permittivity, and permeability is being used. Mu is the permeability used in magnetostatics. For the medium, this is particularly for the medium, the factor epsilon is permittivity, mu is permeability, and the Maxwell's equations. So we are going to do a detailed discussion and analysis of Maxwell's equations in the next sessions, but time being, out of the 4 Maxwell's equations, 2 of the equations are in analogous in electrostatics are del dot D is equal to rho V and del cross E is equal to 0 are the 2 equations among the 4 equations. Del dot B is equal to 0 is the equation in magnetostatic and del cross H is equal to J is the equation in magnetostatics. So you may observe 2 equations with the dot product and 2 equations with cross product. So here in the electrostatics you have with the electric field intensity. In magnetostatics we have the equation cross product between del operator and the magnetic field intensity H bar, and here current density, these are related, and scalar with the V with the potential with the E bar is equal to minus del V is going to give us the potential here, whereas here in the magnetostatic the potential is a vector quantity, whereas in electrostatics the potential here is like a scalar. That is why with the del operator we will represent it as a vector quantity. Minus del V is again a vector potential in the electrostatics. Vector potential in electrostatics is del V. Minus del V, that is equated to electric field intensity. Again, this is a vector and this is also a vector. Whereas in magnetic, vector potential is represented by a bar. A bar corresponds to magnetic vector potential. Del bar is anyway del operator. B is the magnetic flux density. And your energy density or the work done is given by 1 by 2 epsilon E square here in the medium. So in the magnetostatics, M corresponds to anyway magnetostatic related 1 by 2 mu H square. Here square of the magnetic field intensity, here the square of the electric field intensity. So this is the analogy. You see, based on this analogy of electrostatic and magnetostatics, we may understand the concepts very easily. Two important laws for solving magnetostatic field that we use is, one important law is Biot-Savart law, which is applicable to all general cases, whereas Ampere circuital law is applicable for cases of symmetrical current distributions. This is the important one, and we will see the topics like Biot-Savart's law, as this is a third chapter that we are representing. The Biot-Savart's law, then Ampere circuit law, magnetic flux density, magnetic forces, boundary conditions. These are the contents that we are going to discuss. And earlier it used to be that magnetism and electricity were considered as a distinct phenomena, but when Christian has introduced an experiment that showed a compass needle deflecting when in proximity to a current carrying wire, then the concept of magnetostatics came into picture. He used compass to show that current produces magnetic field that loop around the conductor. The field grows weaker as it moves away from the source of current. So here this particular symbol represents current coming out of the paper, and this cross represents the current heading into the paper. So in order to show the directions, we have used these two. So this is a current carrying conductor through which current I is flowing in the Z direction. So the fields around the current carrying conductor are clearly indicated and the directions are indicated with arrow marks. The principle of magnetism is widely used in these fields. Again, magnetic memories, motors and generators, microphones and speakers, magnetically elevated high-speed vehicle, and magnetic fields can be easily visualized by sprinkling iron filings on a piece of paper suspended over a bar magnet. This is a simple experiment. The field lines in terms of the magnetic field intensity H in units of amperes per meter. Magnetic field intensity is represented with amps per meter. It is analogous to the volts per meter units of electric field intensity E. Just now we discussed. Magnetic field will be introduced in a manner paralleling out our treatment to electrostatic fields. And the important law is Biot-Savart law. Biot is one scientist, another scientist is Savart, arrived a mathematical relation between the field and the current, between the magnetic field DH and the current I. They have arrived with this equation. DL is a differential length that was taken in a current carrying conductor of length L. A point P2 is taken at a distance of R12 is at a distance of R12 from this differential length DL1, and here the field differential magnetic field strength or magnetic field intensity is taken as DH. Then DH bar is given by IDL cross producted with a unit vector A12 bar divided by 4 pi R12 whole square. This is what is given. And to get the total field resulting from a current, we need to sum the contributions from each segment by integrating this. So if you take this entire length as L1, you may subdivide these differential lengths like into DL1, DL2, DL3 and so on up to DLN, various N differential lengths. So we need to get the total field due to these differential lengths. How that is possible is integrate all these or sum all these differential lengths. Summation of the differential length, in other words, integration of these differential length. Hence, you got this equation IDL cross producted with AR bar divided by 4 pi R square. And now you have, due to continuous current distribution, so this is your IDL is a line current, and this is a surface current KDS, and this is a volume current. So we may have different current distributions. The current distribution may be in the form of a line current, the current distribution may be like a surface current, or it may be a volume current. And this is represented with IDL and surface current distribution, where the K is your surface current density multiplied with differential surface ds. As a result, you will get I, that is current. So J is over a volume, and this is differential volume. J is the current density over this entire volume. So your units are like ampere per meter cube multiplied with meter cube, that results in amperes. So in terms of the distributed current sources, the Biot-Savart's law comes as, for line current, it is IDL bar cross producted with AR bar divided by 4 pi R square, and the field intensity due to the surface current. The surface current is represented as K ds bar and cross producted with the radius vector AR bar divided by 4 pi R square. Similarly, due to the volume current distribution, JdV is the volume current distribution cross producted with AR bar divided by 4 pi R square. Now you may let us apply the derivation. So whatever the equations we have seen so far, we may try to derive them so that you will have a clear understanding and clear remembering of those equations. To determine the magnetic field H everywhere due to a straight current carrying filamentary conductor of finite length AB, we may apply this. Now, for a filamentary conductor, a current carrying filamentary conductor is taken, its length is AB. So A is this point and B is this point. AB is a filamentary conductor. So AB is a filamentary conductor. And this current that is passing through this filamentary conductor is A, and differential length in this current filament is represented with DL, and the filamentary conductor is placed along Z direction. This is for our comfort that we have taken the filamentary conductor along the Z axis. In this particular derivation, it was taken like that. The start of the filamentary conductor, A, P is the point at which we are finding the field, and the start point of the filament is subtending an angle alpha 1 with the point P, where we are finding the field intensity. And similarly, the upper portion of the filamentary conductor, which is B, we have taken AB here, finite length AB, you observe, this is subtending again an angle alpha 2. Okay, so A is subtending an angle alpha 1 to the point P, where the field intensity is found. B is making an angle of alpha 2 at the point P. So we assume that the conductor is along the Z axis, right, with its upper and lower ends respectively subtending angles of alpha 1 and alpha 2 at point P, where the magnetic field intensity, magnetic field strength H is to be determined. The field is independent of Z and phi and only dependent on rho, as the field direction is along the rho direction. You observe, this is the rho direction. Okay, and you do not have any AZ bar and A5 bar. The term DL is simply DZ AZ. Why DZ AZ? Because the differential length is taken in which direction? In the Z direction. So this DL is taken as dz unit vector along z direction is az bar. So dz is taken as, dl is taken as dz az. So that is what we have written here. And the vector from the source to the test point P, vector from source to the test point P is taken as r bar, clearly indicated. So this is from the vector from the source point to the point P is taken as R. This is what R. And this is given by R is equal to RAR bar. And that is, how do you get? It is the vector summation between ZAZ and rho A rho. Vector summation. So how do you get this R? Is the vector summation between ZAZ and rho, yes, ZAZ and rho A rho. This is what we are talking about. RAR is the vector summation between rho A rho and ZAZ, rho A rho and ZAZ. This is what, rho A rho and ZAZ. So that you will get this. This R, this is R. Okay, rho A rho and ZAZ. We got that here. RAR is this. Where the magnitude can be found, square root of minus z whole square plus rho square, and the unit vector can be found AR bar as minus ZAZ plus rho A rho divided by square root of z square plus rho square is the unit vector along this direction. Now you may combine these terms. You may combine the terms IDL cross producted with the AR bar. In place of AR we have R divided by mod of R. So that is, mod of R is R. So already R square is there. R square multiplied with R cube you will get. Here in place of AR we have R bar by mod R bar. Mod R bar is R taken as R. 4 pi R square multiplied with R will result in 4 pi R cube. In place of R bar we have to substitute. Just now we have discussed, this is the vector summation rho A rho minus ZAZ. That is substituted here, and 4 pi R square is rho square plus Z square whole power 3 by 2. We got it. Cross product of DZAZ with ZAZ plus rho A rho. So A rho and yeah, we have to take the cross product. So DZAZ. So DZAZ is represented here in the here like this. So we have rho, A rho has rho. So we have written here. There is no A5 component in this DZAZ. So 0 was taken. There is a minus ZAZ component that was written here. So this is rho dz A5. And this yields the H equation like this. So DL cross producted with R bar is found as rho dz. So DL cross producted with R bar. In place of DL cross producted with R bar, we have written rho dz. This is what we have done. So simple. Divided by 4 pi rho square plus z square whole power 3 by 2. That is what here. And the direction you observe is A5 bar. Why we got A5 bar is AZ cross producted with AZ is 0. AZ cross producted with A rho is your A5. That is resulting in A5, right? So it is very easy for us to find even the direction of your magnetic field intensity. This is how we can derive the equation for magnetic field intensity or magnetic field strength for a point P located in the XY plane and a filament conductor. For a filament conductor, we have derived the, having a finite length AB, we have derived the equation for magnetic field strength. So this is what the equation. And from trigonometry, you may find tan alpha is equal to rho by z. So go to the diagram and observe where is the alpha. This is the alpha is the angle subtended by this differential length with the point P, and tan alpha is equal to opposite side by adjacent side, and opposite side being tan alpha is equal to opposite side being rho and adjacent side being z. We got tan alpha as rho by z. Again go to the diagram and observe, yeah, this is tan alpha being your rho being the opposite side and this z being the adjacent side for this alpha, rho divided by z. So you have written tan alpha is simply rho by z, and z is equal to, if you want z is equal to rho cot alpha. You got this one. And differentiate dz, we want dz is minus rho cosecant square alpha d alpha, and you may substitute that. Why we are doing this is, here we have dz, we want to still further simplify this one, and dz can be found like this, and substitute that dz value in the equation for h here, so that we may get this equation. And again you may further simplify this. Remember, dou by dou x of cot u is cosecant square u dou u by dou x, and 1 plus cot square u is equal to cosecant square u. If you remember this identities, then it is easy for us to solve this magnetic field intensity equation. And this here cosecant square is, here cosecant cube is there, 1 by cosecant alpha is the resultant, and yeah, you are left with this. Okay, 1 by sine alpha d alpha integral sine alpha d alpha and alpha 1 and alpha 2, and you are left with 1 by 4 pi rho cos alpha 2 minus cos alpha 1, and the direction is along phi direction. And finally you have derived the equation for magnetic field intensity as H is equal to 1 by 4 pi rho cos alpha 2 minus cos alpha 1 A phi. This expression is generally applicable for any straight filamentary conductor of finite length. So this is very important derivation that we may use in problem. As a spherical case, when conductor is semi-finite with respect to P, and A is at 0, 0 suppose, and B is at infinite length, Z is having infinite, you observe B is at 0, 0, comma infinite, or 0, 0, comma minus infinity, then the angle alpha 1 becomes 90 degrees and alpha 2 becomes 0 degrees. For this particular case, the equation whatever we have derived, H is equal to 1 by 4 pi rho cos alpha 2 minus cos alpha 1 A phi reduces to alpha 2 and alpha 1. Alpha 2 you substitute 0. So cos 0, 1. Cos alpha 1 is cos 90 degrees. So this is resulting in a value of 1 minus 0 I by 4 pi rho A phi. So cos alpha is 1 minus 0 is 1 multiplied with I by 4 pi rho, so that is I by 4 pi rho A phi bar. So this gets simplified like this. For a special case, observe. So another special case, you observe. Earlier A is taken, the coordinates of A are taken as all zeros, 3 zeros, x0, y0, z0. Now in this special case again, A x0, y0 and z minus infinity. and B is taken as 0, 0, infinity. Here also B 0, 0, infinity. In this case also B 0, 0, infinity. The angle becomes, in that case, alpha 1 as 180 degrees and alpha 2 as 0 degrees. For that particular case, we can show that H is I by 2 pi rho A phi. And from the previous example, the vector H bar is in the A phi direction. Yes, clearly A phi, where it needs to be determined by simple approach. A phi bar is equal to AL cross producted with A rho, where AL is a unit vector along the line current and A rho is a unit vector perpendicular from the line current to the field point. Okay, we may take a simple example problem. The conducting triangular loop carries 10 amperes and H is we were asked to find H, that magnetic field strength, at 0, 0, 5 due to side 1 of the loop. There are clearly sides are given 1, 2 and 3. Due to side 1, what is the magnetic field strength was asked, and clear diagram was given. 1, 2, 3 are given. 10 amperes is the current flowing. So how do we approach? For our convenience, redraw this one, and for clear understanding of alpha 1 and alpha 2, we have to write this. Okay, and we have to redraw. This is the XY plane. So you have a filamentary current carrying conductor. Side 1 lies on the XY plane and treated as a straight conductor. So side 1, you take side 1 in the XY plane. Okay, done. Side 1 done. And and treated as a straight cut. Join the point of interest 0, 0, 5, where we are asked to find the field is 0, 0, 5. So it is a clear indication the point must be on the Z axis, as only Z coordinate 5 exists. So here 5. So the beginning and end of the line current. So this is the beginning and the end of the line current, and it is taken along the rho direction. A rho is the unit vector along that. AL is the unit vector along the length AL, and alpha 2 is the angle subtended by this point where we want to find the magnetic field intensity. We did it. This will show how H is equal to 1 by 4 pi rho cos alpha 2 minus cos alpha 1 A phi is applied for any straight thin current carrying conductor. From the figure, you know that alpha 1 is 90 degrees. Yes, alpha 1 is 90 degrees. This is 90 degrees. And cos alpha 1 can be found cos 90 0. And from trigonometry, cos alpha 2 can be found out. Cos alpha 2 is equal to your adjacent side divided by hypotenuse. So you may get that value as 2 by square root 29, and rho is equal to 5. And to determine A phi by a simple approach. See, this is one approach we have given. Another simple approach also can be used. Let AL is equal to AX and A rho is equal to AZ, so that A phi can be computed as AL cross producted with A rho, that is equal to AX bar cross producted with AZ, and minus AY, and you may find this as 1 by 4 pi rho cos alpha 2 minus cos alpha 1. Cos alpha 2 we computed as 2 by root 29, substitute that, and cos alpha 1 is 0, as alpha 1 being 90, cos 90 0. So substitute, and you are going to get minus 59.1 along the AY direction, and milliampere per meter are the units. So we'll continue the session on magnetostatics. Okay, in the next class we may again see a few example problems based on the magnetostatics, and we will continue the topics related to the magnetostatics in the next class. So once again I thank Honorable Vice Chancellors of both JNTU Kakinada and Honorable Vice Chancellor of JNTU Anantapur and AP State Council for Higher Education for giving me this opportunity. Thank you. We will meet in tomorrow's session.